starting from random play, no input given, no domain knowledge other than the rules, they generalize AlphaZero to play Go, to play chess, and to play shogi. And within 24 hours, it reached a superhuman level. And what I want to explain you is same as before. I mean, when I see these things, is how. I mean, it's obviously, one might think, well, it's magic, or even worse. I mean, we may have a Terminator state here. But I want to tell you, well, I mean, it's obviously not. And I want to show you how, fundamentally, how simple this is. Like I said, it's a field called reinforcement learning. Basically, in reinforcement learning, how you, it's like it's life. At all points, you have a certain state. Maybe you're hungry, you're sleepy, you're tired, you're excited, you're happy, and at each state, you can perform certain actions. So if you're hungry, well, I mean, you say, well, I mean, I learned that if I'm hungry, I don't want to be in this state. I'm gonna eat. And by each action, you get a certain reward. If you are hungry and then you eat some hamburger and you like it a lot, well, I mean, you're just going to have a really high reward. And then the next time that you're hungry, you will learn, well, I mean, last time I had this hamburger, I liked it a lot and I had a high reward, so I'm going to keep repeating that action. If you do it many, many times, well, I mean, then you will realize that you're in another state where you gain a lot of weight. And you will say, well, I mean, that actually state, I'm no longer happy in this state. This is a low reward state. And what's going to happen is that, well, maybe next time you will have the hamburger, but maybe not that often. You're going to learn that when you're hungry, yeah, having a hamburger is good, but just not that often. So in reinforcement learning, it's the same thing. You have to create a model where an agent knows in which state they are, what actions they can take. And all that the action agent has to do is, well, what do I have to do so I have the maximum number of rewards? That's it. You're not going to teach them the rules of a game or anything else. It's just how to maximize your reward. So I want to show you a couple of examples. Well, actually, first one question. So imagine that this is our very simplistic world. We have a 3x3 grid. Your actions are up, down, left, and right. And the reward of each state is -1, except with this one that has a reward of 100. So, very simple question. If you're in that state, which action do you think you would have to take? Yeah, I'm sorry, I thought it was there. Yeah, you will have to go right. I mean, you just want to move into a state that has higher rewards. So let's do that as an exercise. Can we teach a taxi to pick up a passenger and drive that passenger to the location? And let's simplify the world. We have a grid 5x5 in 4 designated locations. We have designation red, yellow, blue, green. And the taxi can obviously be in any of these states, can drive up, down, left, and right, but it can also do pick up and drop off. Rewards. In this very simple game, every possible state has a -1, with the exception of if you are in the designated destination and you execute the action of the dropping off the passenger. In that case, you're going to have a reward of 20. If you just model that, you can, yeah, for example, yeah, it's a question. So you're the taxi. You're in that square. The drop-off location is G. What action do you think you should take from this the 6 on above? If you have up, down, left, and right, pick up and drop off. You're in this square. This is where you're supposed to drop off the customer. Which action do you think you should execute? Yeah, drop off. Very, very simple. Now, building on that knowledge, almost similar as before, the taxi is on that square. You also have the passenger. The drop-off location is also G. Which action should you take? Yeah, you're gonna go right. So let's think about how many states can we possibly have in this world. So we know that we have a 5x5 grid, so we can be in 25 states. Then the passenger can be at any of these locations, so that's 4. Or the passenger can be with you, so that's 5. And you also have the destination, so that's another 4. So 25 times 5 times 4, 500 states. In this very simple example, if 500 states, how about if we create a big table, 500 states, and for each of them we just learn what action do we have to take. And I want to show you the example of that working. So let me show you. So it just takes a couple of seconds to train. But what I want to show you is so here's our, in this case right now, a random state, here's our taxi, and don't remember either R or Y is the, one of them is the pickup and another one the drop-off. So if I just run this, you see that the taxi says, well, I need to go west. And then it's going south. Here then it means that the Y is the pickup destination. It's going down, it's going down. Once it arrives at that location, it executes the action of pickup, change to green. The taxi has the passenger. And now it's just going north, north, north. And executes the drop-off. All I'm doing right now is for every step, I execute an action. I get obviously a new state, I go into some other place and I get a reward. And I have some a learner that I'm querying it. I'm saying, well, I got into this new state, I got this reward, what action should I take? You saw that after just a couple of seconds, it learned how to go, I was able to teach it to go and pick up a passenger and drop it at destination. I didn't have to say anything else about, well, I mean, what's the fastest way to get to some place, or that it has to pick up and drop off a customer. Now, can we make something a bit more complicated? The one problem in reinforcement learning is, what if the state space is really big? In the example we had before for the taxi, we have 500 states. What if it's really big, like say, something that's continuous? The answer, this is also what is called deep learning for reinforcement learning. We can use the examples that we learned from before. We can use another neural network. The same way that we can use a neural network to say, well, here's an image with a really big density, tell me if it's a cat or a dog. We can do the same thing for reinforcement learning. Here's a state space, something really big, tell me if I should go up, down, left, or right. And I want to show you those examples also with some code. So another exercise, hopefully you have played, it's balancing a pole. All of us have taken that game where we just put a pole or a broom or something, and we want to balance it. So can we teach a computer to do the same? So for instance, in here I have an example. I want to show you first an example where we just go always left. I mean, it's obviously really silly, but I want to show you, well, I mean, we are never all going to be able to balance it if we just go left. But one might say, well, I mean, Carlos, isn't it that just too simple? I mean, what if the pole is just going to the left? Well, should I just take the direction left and then vice versa? I mean, we can have that naive strategy. And we see that it's actually not that simple. It does something. Well, it starts balancing, but after a while, it just falls down. I want to show you an example with deep learning. So with deep learning, you can see it takes a second, it balances, and it just basically doesn't move. At every second, every step, this thing is doing left and right. But you can see it's amazingly really good at balancing that pole. I was able to get to this state with just a couple of minutes of training. And I want to show you one more example, even a more complicated one. So how about if we try to land in the moon? Imagine they have a spaceship. In the spaceship you can fire engines. Here's your little spaceship. It's like an Atari game, and you can fire an engine to the left, to the right, or down, or just don't do anything. So what we want to do is have an agent that can actually land in the moon, and also we want to reduce the number of fuel that we use. So I want to show you first the beginning. So this is when it doesn't know anything. So it's starting to learn. Obviously, you can see that the spaceship is thrown with random force in the environment, but the agent doesn't know what to do. You can see it's firing some engines, does the left and right, but every time it obviously goes and crashes. What it's doing there is, well, saying, I have no clue what's going on. I'm just going to start firing engines left and right. All that we have to do is, hey, robots, whenever you're actually here, that's a high reward state. We also tell them, when you use your fuel, you get penalized. So try to reduce the amount of fuel. But that's it. This one is a little bit more complicated, so it takes a couple of hours to train. But I want to show you how it looks like. I have some pre-trained weights. How it looks like after a couple of hours of training. You can see that spaceship. I don't know physics. I don't know how to play with it. I don't know what's the right combination of left and right engines. All I tell the spaceship, you have these states. This is the actions that you can take, and this is how you get penalized. I think it's just pretty amazing how you can see how it's thrown with random force, different situations. In just a couple of hours, this agent learned how to land. I think I could spend hours watching this thing. Since it's thrown with random force, and it learned how to perfectly land.
How many hours?
This was like a 3 to 4 hours, but I'm pretty sure it can be faster. I mean, this is actually my code, so I'm pretty sure it can be more efficient. This is called deep learning. So, and based on a paper from just a year ago, and there are techniques to make it even faster, but that's from last year. So basically, right now, what it's doing is just taking experience. And you can be more efficient as to how you pick the best experience. But even without all the inefficiencies, in a couple of hours you can see that that thing learns how to land. And well, I mean, to wrap up, I know this is a web apps class, and you might say, well, I mean, Carlos, thank you. You showed me all these cool things. I have a web app to do for next month. And so, like I said, I want to show you the principles of machine learning, showing you that there's no magic behind it, there's no Terminator, and most importantly, that it's actually very basic and simple principles. What I want to do now is just give you three simple cases, APIs, or examples that you can apply to your web app. First one, something is very simple, is sentiment and text analysis. Right now you can have APIs for free. They have a text, pass it into an API, and tell me, well, is whatever I have written there, is it happy? Is it sad? Is it mad? You can obviously think of your web app that can benefit if someone is posting to a forum, you have a forum and you have comments, well, is the people actually talking good or bad? This is supervised learning. As we saw before, you can always map text into labels. You can say, hey, today is a great day. Well, and then you learn that's happy. Today is a bad day, and you know that that's negative. If you give it a lot of samples, it will know how to do sentiment analysis. The best thing is that you don't have to worry about coding it. There's a lot of APIs for free that you can benefit in your application. Another really popular is obviously image classification. You have an image and you can detect, hey, am I seeing a cat? Am I seeing a dog? Am I seeing even a duck? You can train it and get some information, and like the example before, you don't have to code that much. Hopefully that's another idea for your web application. Maybe you have a customer experience or something that you upload an image and you can quickly detect what's in that image. The last one, something also very popular, is chatbots. You can imagine a web application where you have virtual assistants. I'm sure by now all of you have seen it in any web application. If you go to your bank or whatever application you have, they're most probably going to be created by chatbots. They are not that good, but they are getting better. And also a good thing is that there's also free APIs. You define a sentiment, you define the text, and you can have a web application that can talk to a customer. So with that, I wrap up my talk. Thank you. I have any questions, I'm happy to stay. If you want to talk about more your web application or anything, feel free to reach out to me. There's my LinkedIn contact and my email. Thank you so much for your attention. Yes.
So you mentioned in like the December 2017 paper that like they had AlphaGo 0 and they used it to like reapply like chess and like shogi. Is that
yes.
So like now that like Go is like the big problem that was like there for a long time, right? What do you think is the next game that people are looking to solve?
I don't know. I don't know of games. I can tell you what are the problems.
Okay.
So right now the problem that the problem that is still not fully solved is what that is doing is combining supervised learning and reinforcement learning. In supervised learning, I show you that, say you have a lot of examples and you say, well, I mean, this is a man, this is a woman, this is a man and a woman. Learn something and then you can use it to predict. Then in reinforcement learning, and the basic example is, well, define all the state space and learn for each state what action should I take. So the problem in reinforcement learning is that when the problem grows, the state space is really, really big. So you cannot have a table we're able to define a table of 500 elements, rows. You can have a state space for, I don't know, millions and billions of states. And the solution that these guys found out is, well, how about if we take a neural network and start learning the action for each state? And that works really well, but how it works is that at the beginning we don't know anything, and we're feeding it things that we don't know. We have a state, a table, and we say, well, I mean, I don't know how the spaceship should go, but I think I landed that there, and I think that gave me a good reward. So go there. And you feed that into a neural network. The thing is that when you're feeding that into a neural network, it's still incomplete. How can I say it? It's incomplete information. So it's something chasing to something else. So it's very hard to converge. So right now, I would say that's one of the still unsolved problems. That basically you're feeding information to a neural network that you don't know it's good, and magically right now, I can say magically, keeps getting better, but it's still not very well understood why, and might not converge, or even if it converges, then it can just diverge. It's a great question. I don't know the game, but I know the problems.
I have a question about also the AlphaGo master paper.
Yes.
Like, so I didn't read the paper, so I don't know what they actually did. I know that in the original AlphaGo they had two networks, right?
Yes.
And one network was to evaluate the states, like is it the winning state, is it not the winning state, and they also have like a random walk and a decision tree or something like this. How is this different? Is this like something completely different? Like everything is a big network, or how does it work?
So in this case, I don't know for the AlphaGo. I know for the AlphaGo 0.
Yeah.
So it's what you're describing is it's again everything maps out to figure out what state I am in and think what's the best action that I can take. The challenge, something is called, and the challenge in reinforcement learning is the exploitation versus exploration dynamic, which is what you were saying. So at the for example, reinforcement learning resembles a lot real life. So imagine that you again are hungry, and you say, well, I mean, but I'm hungry. I don't know what I do. Should I do? I go and eat a hamburger, right? And you feel good. You say, hey, well, I mean, that's what I have to do. After a while, you probably will gain weight, and you say, well, I mean, I was doing something wrong. The thing is that if your agent just keeps eating hamburger, how can it ever learn that there are other things in life? So at one point, you have to say, I'm in a state where I'm hungry. I know that my action is eat a hamburger. Is there something else that I can do? Every once in a while, you have to start exploring. That's what AlphaGo 0 is doing. I don't know the AlphaGo, but the AlphaGo 0, that's what it's doing. Is at every state, do something. Every once in a while, try something else and see what's better. Yes?
Yeah, so if you're given a problem, how do you know, or how do you know which algorithm to choose? Understand different algorithms. Just try each one and see which one has the best effectiveness?
Pretty much. To the best of my knowledge, that's what I've done, and that's what I've learned. So definitely neural networks is defined to be right now one of the best ones, but it's still not the silver bullet. So you have caveats. First, like you said, there are obviously heuristics or recipes to say, well, I mean, if you're in this example, try this, but there isn't a silver bullet. I show you K&Ms, nearest neighbors. That's actually really simple, and the advantage of it is that the problem can be extremely complex. The solution is really simple. You don't need to create functions. You say, well, I mean, for instance, when you buy a house, how do you predict the value of a house? I mean, it can be a really complex problem that it gets, for instance, you can say, how many rooms do I have, how many bathrooms, what's the state, And it maybe boils down to know what's the houses that you have next to you. That's the answer. You don't need a neural network. You don't need a decision tree. And even within a neural network, there's a lot of, I would say, art into it. It's ironic that there isn't good guidelines as to, well, how many layers you should have or how many neurons you would have. So yeah, the answer is still kind of art.
Alright guys, we're running short on time. The next module lecture is going to be at 12:30 and we have lunch for you guys, so